and so that, at this point here, probability density is 0, right? So you won't find the particle here. And similar argument here and here and so on. So, all right. Well, that's the end of the theory session for this chapter. Now I'll combine, because this is rather quick. I'll do 2 questions for the problem solving, which I'll just combine with this session, because there are only 5 questions at the end of the chapter, and I'll do 2, just more or less my usual amount. The first one is it's in the context of the infinite square well, right? So you're in the x-axis at A minus A, you have 2 barriers, and outside that region the potential is infinite. Okay, so the infinite square well, and bit of revision. The wave functions were of this form. We've done this before, so go back a couple of sessions and revise. Okay, so if n is even, your waveform. If n is even, your wave function takes this form, so it's 1 over root square root of a times sine n pi x over 2a, and if n is odd, then your wave function is 1 over root a cosine n pi x over 2a. Now you're asked to find the average value in that 2a area, so between a and minus a. You're asked to find what is the average value of x squared. Now, the notation here will be new to you. This is why I'm doing this example, because there's a little bit of theory in a sense. When you see these angular brackets like this, it's asking you to find the average value of. This u squared here, remember from Born, that is the probability density. Right? Now, can you see that if you want to find the average value of x squared, you integrate it. The value you're trying to find the average of, in this case x squared, you integrate that value, whatever it is, times the probability density dx. This is from statistics. I hope you've done enough statistics. So to find the average value of some quantity, here's your quantity here, you integrate that quantity by the probability density. Now, if that's totally new to you and you haven't a clue what I'm talking about, I suggest have a look at some undergrad statistics, maybe even a fresher level. So this is the probability density for your function x. Okay, in this case we're talking quantum mechanics, so our probability density is just the wave function squared. Okay, so to find the average value of x squared, our probability density is just u squared, the wave function squared. Okay, now u is nothing outside the limits a minus a, so the minus infinity to infinity, the usual limits, well, u is 0 for most of that. So the limits become minus a and a. Right? So effectively, what we have to do is find, calculate what this is. Right? Now let's see. So now we know the u. We've got given 2 values for 2 cases when the integer n is even or it's odd. So I've written, u squared just becomes either that squared or that squared. So I've written it here like 2 cases together, save a line. Now, in the text, there's an appendix. I think appendix E. I'll show you just sort of. So appendix E, it's called useful integrals. Right? You're just given some useful integrals, and I've used one of them here. And I mean, you could calculate this out the hard way using integration by parts and whatever, but anyway, they're just given. So what you're given is that x squared sine squared n pi x over 2a dx is equal to a cubed over 3 1 minus 6 to the minus 1 to the power n all over n squared pi squared. Now if it's cos squared here, if you have x squared cos squared, then you get a plus here. It would be plus 6 times minus 1 to the n. Alright, now you've got two cases. So let's do it for this case, with a sine case. So n is even. Okay, so n is even. So minus 1 to an even integer is plus 1. So you'll get a minus 6 here. You just get minus 6. Alright, now if it's cos, that's this case, n is odd. Okay, and so you'll have a plus here because n is because of cos squared. So you'll have a plus here. But n is odd, so minus 1 to an odd number is minus 1. But you've got a plus here, so it'll be minus 6. So in both cases, the answer, you'll have 1 minus 6 over n squared pi squared. Now you're squaring the u, right? So you've got this 1 over square root of a. So when you square it, you'll get a 1 over a term. And now here you've got a cubed, and the answer is a squared, and so an a has disappeared, and that's due to this. When you square that, you get an a underneath. So a cubed divided by a, and there's your answer, right? And it's the same answer for both cases. Doesn't matter whether it's the sine or the cos. It doesn't matter whether n is even or odd. Right? There's your answer. All right. The second question we largely did in the theory section, and the context this time is the square well. It's not the infinite square well. It's just the square well. So that meant so here's your barriers at plus a and minus a. The potential outside that region is not infinite, it's finite. So V naught, value V naught. Right? So in that context, and in the case of odd parity, right, so your wave function, its parity will be odd. In other words, u of minus x equals minus u of x, right? Odd parity. Okay. You're asked to show there'll be no bound state. That means there's no eigenfunction within that range, plus or minus a. Bound means stuck in, right? If v naught a squared is less than pi squared h bar squared divided by 8m. Now that should ring a bell, right? That came up in the discussion of why there was no ground state energy. There was no discrete energy for the case when your gamma here. Remember this? Remember the series of curves we had what I was calling the square root thing. So square root of gamma over x all squared minus 1, and the cotangent. Now the lowest value gamma can be to get an energy. A discrete energy and an allowed energy, was when this curve stops here at value for x at pi over 2. Remember that from the theory? Now you could, for lower values of gamma, you have curves come here and they stop on this line, but then there's no intersection point, no cutting point with the cotangent curves. So you need to have one of these gamma curves, if you like, cut at least one of these cotangent, well actually it's minus cotangent of x curves. And the first time that happens is when your gamma equals pi over 2, and there's your intersection point, because these two curves have the same value at that point when x is pi over 2. Right? Well, from the Heisenberg uncertainty principle argument that we did in the theory, you can use that in reverse, in a sense. If, well, what was the logic? That you get the Heisenberg uncertainty relation is violated if your V naught A squared is less than that. Right? Go back to the theory. So your Heisenberg, your HUP is violated if this is true. Okay. And well, that's a no-no. That's not allowed. So you cannot have this. So if your VA squared is less than this, that's the smallest amount that's allowed for this. That gives you a solution. Now remember, we derived this number here based on gamma equals pi over 2. So if gamma takes a smaller value than this, there's just no connection. There's no cross point. There's no meeting of a gamma curve and a cotangent curve. This meeting happens for the first time where there's just only one allowed energy that corresponds to when x is pi over 2. So if gamma is less than that, no allowed energies. Right? So and these values, V naught A squared comes out of x. You can deduce that from the value when x equals pi over 2. So so question 4 we sort of more or less did in the theory section. So that shouldn't, if you followed the theory, that shouldn't be too hard. Right, well that's the end of the problem solving session, the end of this lecture. And as I was saying a bit before, lecture 3, fairly short lecture, followed by lecture 4, which is a long one. But lecture 3 is essentially, I mean, it'll still be about STI in that context. In fact, there are 4 chapters on that, on Schrödinger time-independent equation. But it'll be introducing a very useful mathematical trick device invented by Dirac called the delta, D-E-L-T-A, delta function, which I'll just mention quickly. A delta function is sort of like a spike, right? It's infinitely thin. It's a function. It's infinitely thin and it's infinitely tall, but such that the area under that spike is 1. Right? And the mathematicians didn't like this idea from the physicists at all for a long time, but it was just so useful that they sort of grudgingly accepted it. I think since then things have been cleared up a bit by the mathematicians. They're now happier. They've redefined this delta function in a way that they feel is sufficiently rigorous. Anyway, that's a side issue. Okay, so till next lecture.